If China lands astronauts on the moon prior to the U.S., it will be a shame to America, said J.D. Mukherjee, an ex-Xavierite, and currently director of NASA Florida Space Grant Consortium. Mukherjee made this statement during a presentation titled Humanity's Return to the Moon at Nehru Planetarium at Worli, Mumbai, Saturday evening. On October 29th, the China Manned Space Agency announced the 2030 target for the crewed lunar landing mission, and on September 28th unveiled the spacesuits to be worn by astronauts on the moon. Pause for a few seconds and support me with a subscribe. He said that a Chinese landing on the moon before the U.S. would help to enhance funding for the American manned lunar program. The consortium, formed in 1989, augments NASA's educational outcomes and is administered through the University of Central Florida and the Florida Space Institute. He did not mince words when he told the audience that if certain technical issues and cost overruns were not solved, NASA's target of a manned lunar landing by the Artemis III mission in 2026 would slip. The technical issues related to the Artemis I mission, NASA's unmanned flight to the moon, launched on November 16, 2022. During the high-speed re-entry on December 11, 2022, at 25,000 miles per hour, the spacecraft's heatshield suffered an unexpected damage, and NASA is still trying to solve the problem. As if this were not enough, NASA's Deep Space Network at Goldstone in California lost contact with the spacecraft for 4 hours on November 23, 2022. In addition, during liftoff of Artemis I, the launch pad itself got damaged and blew away the elevator doors. According to Mukherjee, the cost of repairing them is exorbitant. A report of NASA's Office of Inspector General Office of Audit says, the Artemis program faces schedule, procurement, technical, and funding risks. Where on the moon NASA places its nuclear reactor isn't simple. The nuclear reactor must be close to accessible, extractable, and refinable water ice deposits. In a bold, strategic move for the U.S., Acting NASA Administrator Sean Duffy announced plans on August 5th to build a nuclear fission reactor for deployment on the lunar surface in 2030. Doing so would allow the United States to gain a foothold on the moon by the time China plans to land the first taikonaut, what China calls its astronauts, there by 2030. Apart from the geopolitical importance, there are other reasons why this move is critically important. A source of nuclear energy will be necessary for visiting Mars, because solar energy is weaker there. It could also help establish a lunar base, and potentially even a permanent human presence on the moon, as it delivers consistent power through the cold lunar night. As humans travel out into the solar system, learning to use the local resources is critical for sustaining life off Earth, starting at the nearby moon. NASA plans to prioritize the fission reactor as power necessary to extract and refine lunar resources. As a geologist who studies human space exploration, I've been mulling over two questions since Duffy's announcement. First, where is the best place to put an initial nuclear reactor on the moon to set up for future lunar bases? Second, how will NASA protect the reactor from plumes of regolith, loosely fragmented lunar rocks, kicked up by spacecraft landing near it? These are two key questions the agency will have to answer as it develops this technology. The nuclear reactor will likely form the power supply for the initial use as lead moon base that will support humans who'll stay for ever-increasing lengths of time to facilitate sustainable human exploration of the moon, using local resources such as water and oxygen for life support. And hydrogen and oxygen to refuel spacecraft can dramatically reduce the amount of material that needs to be brought from Earth, which also reduces cost. In the 1990s, spacecraft orbiting the moon first observed dark craters called permanently shadowed regions on the lunar north and south poles. Scientists now suspect these craters hold water in the form of ice, a vital resource for countries looking to set up a long-term human presence on the surface. NASA's Artemis campaign aims to return people to the moon, targeting the lunar south pole to take advantage of the water ice that is present there. In order to be useful, the reactor must be close to accessible, extractable, and refinable water ice deposits. The issue is we currently do not have the detailed information needed to define such a location. The good news is the information can be obtained relatively quickly. 6 lunar orbital missions have collected, and in some cases are still collecting, relevant data that can help scientists pinpoint which water ice deposits are worth pursuing. These datasets give indications of where either surface or buried water ice deposits are. It is looking at these datasets in tandem that can indicate water ice hot prospects, which rover missions can investigate and confirm or deny the orbital observations. But this step isn't easy. Luckily, NASA already has its Volatiles Investigating Polar Exploration rover mission built, and it has passed all environmental testing. It is currently in storage, awaiting a ride to the moon. The VIPER mission can be used to investigate on the ground the hottest prospect for water ice identified from orbital data. With enough funding, NASA could probably have this data in a year or two, at both the lunar north and south poles. Once NASA knows the best spots to put a reactor, it will then have to figure out how to shield the reactor from spacecraft as they land. As spacecraft approach the moon's surface, they stir up loose dust and rocks called regolith. It will sandblast anything close to the landing site, unless the items are placed behind large boulders or beyond the horizon, which is more than 1.5 miles, 2.4 kilometers away on the moon. Scientists already know about the effects of landing next to a pre-positioned asset. In 1969, Apollo 12 landed 535 feet, 163 meters, away from the robotic Surveyor 3 spacecraft, which showed corrosion on surfaces exposed to the landing plume. The Artemis campaign will have much bigger lunar landers, which will generate larger regolith plumes than Apollo did. So any pre-positioned assets will need protection from anything landing close by, or the landing will need to occur beyond the horizon. Until NASA can develop a custom launch and landing pad, using the lunar surface's natural topography, or placing important assets behind large boulders, could be a temporary solution. However, a pad built just for launching and landing spacecraft will eventually be necessary for any site chosen for this nuclear reactor, as it will take multiple visits to build a lunar base. While the nuclear reactor can supply the power needed to build a pad, this process will require planning and investment. Human space exploration is complicated, but carefully building up assets on the moon means scientists will eventually be able to do the same thing, a lot farther away on Mars. While the devil is in the details, the moon will help NASA develop the abilities to use local resources and build infrastructure that could allow humans to survive and thrive off Earth in the long term. Take a moment and give us a like for this video. Thank you so much. Analysis of previously untouched preserved core samples from the mysterious light mantle landslide shed light on what caused this huge tumbling of rocks. A mysterious lunar landslide might be the product of large chunks of debris from the impact that formed the crater Tycho slamming into the side of a moon mountain. The light mantle, which is a bright 5-kilometer long, 3.1 miles streak, emanating from the base of a 2 km tall, 1.2 miles mountain called South Massif, was a key target for NASA's Apollo 17 mission in 1972, with geologist Harrison Schmitt as a member of the crew. Apollo 17 returned from the moon with 243.6 pounds, 110.5 kilograms of rock samples, including 2 core samples from the light mantle. There was so much material in the samples that some of it was kept away, stored, and sealed, until the time came that scientists had better technology with which to study the samples. That time is now. NASA were really forward-thinking during the Apollo missions to put some samples aside, said geologist Giulia Magnarini of London's Natural History Museum in a statement. They were stored so that they could be studied using more advanced technology and new scientific approaches that hadn't even been thought of at the time. The origin of the light mantle landslide is a mystery, partly because it is the only known landslide on the Moon, meaning that we have nothing to compare it to. It's described as a long run-out landslide, as the debris that rolled down the mountain spilled out for a long way onto the Taurus-Littrow Valley. But what carried it so far is also uncertain. Using modern micro-CT scanning, which employed medical-level scans on the previously untouched core samples from the light mantle, Magnarini and her colleagues investigated clasts, which are rocky fragments that broke off from the slope of South Massif. They then compared the shape and composition of the clasts with what was predicted by computer models. The clasts tell us a lot about the process of the landslide itself and how the material within it has been transported, said Magnarini. We saw that the finer material coating the clasts in the core comes from the clasts, and not the surrounding debris, suggesting that the clasts broke up and helped the landslide to flow more like a fluid. This would explain why the landslide produced such a long run out. But what triggered the landslide in the first place? Magnarini's best bet is the formation 108 million years ago of the landmark lunar crater Tycho in the Moon's southern hemisphere, far from Apollo 17's landing site. Tycho is famous for its bright rays of ejecta material that cover a large area of the Moon's southern hemisphere, and there are chains of small secondary craters leading away from Tycho, produced by large chunks of debris from the main impact falling back down onto the lunar surface. One of these chains points in the direction of South Massif, and despite the distance, Magnarini thinks that a chunk of debris from the Tycho-forming impact flew halfway around the Moon and crashed into South Massif. It has been suggested that some of the material thrown up by the creation of Tycho might have struck South Massif, said Magnarini. This could have triggered the landslide that ultimately formed the light mantle. Tycho's young age fits the bill. An older landslide would have been eroded away by micrometeorites long ago. That might be why we no longer see other landslides on the Moon. Impacts like Tycho are very rare now, compared to 3.5 to 4 billion years ago when most of the Moon's craters formed. Overall, Magnarini sees her research as helping to bridge the Apollo missions. With the current Artemis program and NASA's plans to return astronauts to the surface of the Moon, we've learned so many lessons from these samples about how to preserve, store, and open lunar material without damaging the contents. Sighed Magnarini. This is already feeding into plans for Artemis science and helping to develop new instruments. As we delve deeper into the secrets unlocked from those Apollo 17 samples, preserved like time capsules from humanity's boldest era, it's impossible not to feel a surge of awe and urgency. A colossal landslide on the Moon, triggered 108 million years ago by debris hurtling from the Tycho crater impact halfway around the lunar globe. This isn't just ancient history, it's a visceral reminder of the Moon's violent past, where cosmic collisions reshape worlds in an instant. Giulia Magnarini's team at London's Natural History Museum used cutting-edge micro-CT scans on these untouched cores, revealing how rocky clasts fractured and flowed like a fluid, explaining the light mantle's astonishing 3.1-mile sprawl. Such insights aren't mere trivia. They fuel our drive to return, arming Artemis explorers with knowledge to navigate treacherous terrains and harness lunar resources. But let's confront the stakes head-on. With China testing its Lanyu lunar lander in August 2025, and steadfastly marching toward a 2030 crewed touchdown, complete with the Mengzhou spacecraft, Tansuo rover, and advanced suits, the U.S. cannot afford complacency. Their progress, including partnerships for a lunar research station with Russia, echoes the Cold War space race, but this time, the prize is sustainable presence on another world. NASA's Artemis II, now slated for April 2026 with astronauts Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, looping the Moon, is our crucial next step, humanity's first deep space crewed flight in over half a century. Yet delays plague Artemis II's landing, pushed to mid-2027 amid technical hurdles like heatshield fixes and Starship integration. Enter the game changer, Acting Administrator Sean Duffy's August 2025 directive to deploy a 100-kilowatt nuclear fission reactor on the Moon by 2030. This isn't fantasy, it's essential. Positioned near polar water ice for resource extraction, shielded from regolith blasts. It promises unwavering power through lunar nights, enabling bases, Mars prep, and self-sufficiency. As a lunar mission veteran in spirit, I feel the pull of destiny. This reactor could secure America's lead, turning rivalry into inspiration. Picture U.S. astronauts mining ice, fueling dreams, while China's takonauts approach. The Moon calls us back, not just to compete, but to unite in wonder, pushing boundaries for generations. Failure to act? Unthinkable. Success? It ignites the stars within us all.